You've decided to go sledding. What a great idea. So you start off 10 meters at point A, 10 meters above the bottom of the hill. So your initial height is 10 meters measured from the bottom of the hill. That's not the distance you're going to go, it's just the vertical height. You start at rest. You scoot on, so that's point A. You scoot on down. We're going to ignore friction. That's because you're on a sled, so friction is negligible. You're sledding on down. I want to figure out your speed at the bottom of the hill. And then, just for the heck of it, you come back up over this little slope and you end up 3 meters higher. Right here, what's your speed at C? And then if you're really having a good time, you go off in the air. Ah! So, this is an energy conservation problem. As long as there's no friction, energy is conserved. What that tells us is that the energy at A equals the energy at B, which equals the energy at C. The energy is constant at any point along. Because there's no friction doing any work against you. Normal force doesn't do any useful work because it's always at 90 degrees to the direction of motion. And the cosine of 90 is 0. An interesting point about this problem is you cannot really solve it using kinematics because the acceleration, at least the kinematics that we learn in honors physics, because the acceleration is forever changing because the angle changes. And remember, those kinematic equations we developed are all for constant acceleration. So this is a great use of energy conservation here. So to find the energy at B, well, the energy at A equals the energy at B. The energy at A is kinetic plus potential. The energy at B, kinetic plus potential. Anything that has a 0 associated with it, we can cross out. Well, it starts out at rest, and so the energy of motion is kinetic, so it doesn't have any because it doesn't have any speed. Remember, kinetic energy is 1/2 mv squared, and there is none, so that's 0. It has just potential energy at A. At the bottom, at B, it has no height, and the energy of height is gravitational potential energy. It doesn't have any because it has no height. So that simplifies the question. This is mass times g times that position, 10 meters. This is 1/2 mv at b squared. Notice that the mass cancels. And then solve for the velocity at b. That's going to end up equaling 2 times g times that height of 10. I multiply the 2 over to the other side, take the square root. Here's your g, and ya is 10. So that's going to be, well, let's see here. The square root of that is 14 meters per second. Now, what's the speed at C? Well, it's going to be less than that because as you go up, you're going to gain some height. Well, you can do one of two things. You can compare the energy at B, which is all kinetic, to the energy at C. Or you can compare the energy at A to the energy at C. Either one will work. So I'm going to just compare A to C. That, as you already know, that is all gravitational potential. Right, this right here. We crossed out the kinetic because it had no speed at the very beginning. And then at C it has some height, and the rest is going to be speed. So it has kinetic energy at C, and it has potential energy at C. So this is m times g times ya. This is 1/2 mvc squared. That is m times g times yc. Cancel out the masses and solve for the speed at C. this ends up with this equation. You can just put in the numbers and solve if that's easier. It ends up like this, though. 2, I'm just simplifying here. I multiply by 2, bring that to the other side, and it's the difference between those heights. You know, if they went back up to 10 meters, it would come back to a stop, and that would be 0. But it doesn't go back. So if those are 10 and 10, that would go to 0. It doesn't, though. Again, if you don't understand this equation, just put the numbers in and solve for v squared, and then take the square root. That's fine. This is the square root of 2 times 9.8 times 10 minus 3. And dun, 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 dun. That's 11.7 meters per second.